Okay, recording has started. Okay. As we said before, list queue implements the queue interface, and queue interface is iterable. So an iterator should be implemented for complete implementation of array queue. And for this implementation, we have to have an inner class iterator, right? Iter is the name of the class. And it keeps two pieces of information. One is count, another one is index. Index keep the index of the next element to be returned. And it is initialized to be front at the beginning, so it will start from the front and go until the rear, right? And count will keep the number of elements that is to returned, that is accessed so far. And this, when this number of elements is equal to size, we have finished. So there is no next element. And here, as you see, oh, I didn't. Okay, here as you see, while count is less than size, we have next element. When the count is equal to size, we don't have more elements, right? So simple constructor for iterator that initializes index with front, and simple has next method which checks whether count is less than size or not, right? Constant time operation. And here we have the next method, implementation of the next method. In next method, we check whether we have next element. If we don't have next element, no such element exception is thrown. Otherwise, an element at index position will be saved as return value and return at the end. And index and count are incremented. But while incrementing index, we should be careful since it is a circular array, right? And this operation is constant time operation as well, since everything takes constant time here. There is nothing more than constant time. And as far as remove method is concerned, we throw an exception, unsupported operation exception in remove, since we do not like to implement remove operation. Removing an element at in the middle of the queue is not supported by the regular queue structure. So it violates the queues contract. So we do not want to implement it. And one way is this one, throwing an unsupported operation exception. Okay. So as far as the computation time is concerned, all implementations are very similar. Removal is always takes constant time, but adding a new element depends on the implementation For array implementations, we need reallocation, so we may need reallocation. So in the worst case, it may take linear time, but if we perform amortized analysis, it's still constant time operation since the time of the reallocation can be distributed into next and insert operations, right? And constant time is comes for all for the share of each operation. So it takes constant time, and their share for reallocation is constant time. The overall running time will be constant time for each insertion operations, amortized constant time. Okay, as far as the running time is concerned, they are not very different. You can prefer any of them. But when we come to space complexities, linked list implementations require extra space for the links, next and previous. But single linked list just requires the next link, so one link for each element, while double linked list requires two links for each element. So besides the data references, when you consider data references as well, the storage requirement of the double linked list is 1.5 times more than single linked list. It's clear, right? We need 3 references here, 2 references here, so it is 1.5 times more than single linked list. Then you consider array implementation. In array implementation, the capacity is incremented when a new addition requires, there is no place for the new addition. So when we reallocate, almost half of the array is empty. So it is very similar to linked list if half of the array is considered to be empty. So the storage requirement of single linked list and circular array can be considered very similar, while double linked list requires more storage than both these implementations, single linked list and circular array. Okay. Of course, if the if the circular array is full, size and capacity are same, then each element in the array is used. In that case, single linked list stores twice as memory as the circular array. But this is a special case. This is the best case. In the worst case, on the other hand, after several removals, the array can be empty. There is no Q data in the array, right? That's also possible. But as I said before, in an implementation in a software, the storage requirement is the is analyzed with the worst case storage requirement. In the worst case, the storage requirement of the single linked list and circular array is very similar. Okay, this is the last implementation of queue. We have another interface, DAC interface. As you all remember, let me go all the way back until this one. Yes, here we have a DAC interface as well. DAC interface implements the queue interface, and linked list is actually implementing queue interface, the DAC interface, and in that way it implements queue interface actually. So DAC interface, it has more functionality than queue interface, and it is iterable, as you can imagine, right? And now we are gonna talk about this DAC interface. Okay, let me take some time. Okay, let me come to this point. Okay, now we are gonna talk about that DAC interface. DAC means double-ended queue. In that double-ended queue, we can insert and remove from both ends. Remember, in regular queue, we insert a new element in one end and remove an element from the other end. In stack, we insert and remove from the same end. But in DAC, it's more general abstract data type, which allows insertion and removals from both ends. Okay, in collection hierarchy, we have two DAC implementations. Array lists, we have seen in that hierarchy before in a minute, in a minute ago. And we have another implementation, array DAC. Array DAC uses array, actually circular array, to implement DAC interface. Linked list uses double linked list, as you remember. And array DAC is recommended since although it has that reallocation problem, time to time insertion may take linear time, the performance of array DAC usually better on average or amortized better than linked list, since we do not allocate and deallocate new nodes each insertion and deletion as in linked list, and that allocation creating a new node and removing an available node takes a lot of time. It requires garbage collector to run in removal, and it takes time. So array DAC's performance is better, although they both have same asymptotic performance and provides all the information, all the operations in constant time. In array DAC, it's amortized constant time. We recommend array DAC to be used since it performs better. Okay, These are the operations in array DAC and DAC interface. As you see, we have two offer methods, offer first and offer last. Performs the same operation in both ends. Offer first inserts the item at the front of DAC. Offer last the rear of the DAC. And it returns true or false based on the success of the operation. At first and at last are similar, but in that case, an exception is thrown if the operation is not successful. This poll and remove methods are similar. In poll method, we return null if the DAC is empty, and remove returns exception in that case. Poll first and poll last removes element in the front and or rear of the DAC, of course. Similarly, remove first and remove last. Peek operations are very similar. Peek and get. Get returns exception. Peek returns null if there is no element in the DAC. And they return first or last, front or rear element in the DAC. Okay. So we have remove first occurrence and remove last occurrence of an object. These are for removing any element in the DAC. So in DAC, it is allowed to remove an element by specifying the element. Both these methods have an element as a parameter, and it returns true if the removal is successful. If there is an element in the queue, the removal is successful, as you can guess. And iterator method, it returns an iterator since DAC is an iterable. There is one more we are not able to see, which is a decreasing iterator. So we can get an iterator in decreasing order as well. From front to rear or rear to front. Okay. So these are how the operations are, effect of the operation, offer B, offer Y, then we offer last, then add last, adds at the end, and add first at the beginning, etc., etc. You can easily guess the result. Okay, by using DAC, we can you can use DAC as a queue. Actually, DAC extends the queue interface. So anything available in the queue interface should be available in DAC, and all the operations in queue interface can easily be implemented by the operations here in DAC, right? For example, for push, we can use add first. For pop, we can use remove first, right? There is a problem. This is for the stack. Excuse me. Push and pop for the stack, right? Queue operations can be implemented as well. And stack that can be considered as a stack as well. And push can be implemented by add first, and pop can be implemented by remove first. Actually, we just delegate these operations to these methods, or we can use these methods and consider DAG as a stack. Since we do not have all the functionality of vector in DAG, it is more restricted than vector, and that's why using DAG is more preferable than using vector to be able to get a stack. So if you need a stack, probably using DAG would be better. Okay, this is an example for using Q example application. It's a case study, so I would like to leave this case study for you to read. Please read this case study. You can learn from this case study a lot. First, it talks about a simulation, so you can learn a little bit about simulation here, and it analyzes the problem and gives some design details, and at the end the implementation. So by looking at this case study in detail, you can learn what you should provide in the homeworks as well. So it is better to look at this case study in detail. Okay, this is it for today. This is the end of the presentation. So I will stop here, and as you